Okay, so now I want to talk about what I'm sure is the Hindu's most important contribution to science. It's the Hindu-Arabic number system. So this is our system that we use today to represent numbers, to do multiplication, it does not take a PhD in mathematics to make that calculation. But 1,000 years ago, 2,000 years ago, you probably would have required something like an equivalent of a PhD to make a calculation like that. Because in almost all of the other number systems, doing arithmetic was very, very cumbersome. It's really, this is such an important development that I want to really emphasize this point. Okay, so what kind of number systems had been around before that? Well, the Egyptians used some kind of hieroglyphics, 1, 2, 3, and then they had various symbols for things. The Greeks ended up, they had different systems also, but they ended up assigning, I don't know what exactly it was, but they had Greek letters representing different numbers, including numbers for 10 and 20 and 100. So there would be, various Greek letters. There's not these ones, but some ones. Okay, and then if they wanted to write something, they would have to sort of, 2 times 20, and then 3 times 100. Thousands were represented by some kind of dash that you put somewhere. Okay, it was all very cumbersome. Of course, we know the Romans gave us, this system here, which lasted for a long time. It was also essentially hieroglyphic. 1, 2, 3 are like this, and then 5. The Romans used this hand signal. 1, 2, 3, 4. That was 4. That was 5. And from the V that the thumb forms, that's where the 5 comes from. Okay, so if you want to teach a young person how to do multiplication with Roman numerals, you will find it very challenging. It's very hard to explain what goes on. You can't do it sort of systematically because the numbering system is not very systematic. The Chinese had also a system. They had counting boards or counting tablets. Abacus eventually was an important tool for doing computation. And no doubt there might have been some connection between the Chinese and the Indians. But in any case, around the year 600, we don't know exactly when, around the year 600, the Hindus developed this system where they used the numbers 1, 2, 3, 4, 5, 6, 7, 8, and 9. And then in the next couple of hundred years, around 800, they developed the system that we now use, where the place of the digit denotes the power of 10. And that required an important innovation that they didn't have around 600. That requires a separate symbol for 0. So when we write 405, this means 5 ones, 0 tens, 4 hundreds. You have to have the idea that there's going to be an empty place, and you've got to put something in that empty place so as not to get confused with 45. And nowadays it seems like a very inconsequential thing to us, but it was an incredibly important advance that we're going to actually have a symbol for 0. We're not just going to leave it blank. We're going to write something down that's going to represent 0 that allows us now to have a proper place for every power of 10. That is such an important advance in the history of science. I can't think of anything, not development of calculus or Einstein's theory of relativity or quantum mechanics. Nothing else comes close, in my view, to the importance of this in terms of our modern world. Because it allows young people to learn how to manipulate quantities. to understand quantities, and to be able to manipulate them. So we don't actually know who was responsible. It probably, a lot of people contributed. I've heard theories that the language Sanskrit is somehow naturally makes this a very natural thing to do, which very well could be. But this system was taken over by the Arabs, or adopted by the Arabs. And so they're the next people that we need to talk about, the Arab culture. So the Arab, when we talk about the Arab culture, we're talking about a phenomena that has had a very particular birth. Around the year 600, Prophet Muhammad introduced Islam, united these desert Bedouin tribes, and off they went and conquered much of the known world at the time. Right? So there was an incredible spread, exponential spread, and suddenly all of North Africa, a good part of the Middle East, was under their control. And then there was then a sort of a roughly a 400 or 500 year period, 500-year period of Arabic Islamic predominance, where the center of learning in the world was really in the Islamic countries. So because they were originally a tribal Bedouin people, they were very good at assimilating knowledge from the people around them. They imported the works of the ancient Greeks. They valued the works of the ancient Greeks a lot. They ended up taking Alexandria, of course, and so they were able to incorporate the Greek world in the areas that they conquered. But they also took the Hindu works, and they translated them, they studied them, and they ended up commenting on them, and in many cases going further than them. So there are a whole string of important Islamic mathematicians. Their names are sometimes a little bit hard to pronounce and spell, but some of them are Muhammad al-Khwarizmi, around the year 800. Al-Biruni, around the year 1000. Muhammad al-Buzjani, year 1000. And the most well-known name, because he was, I'm not sure, there's also a famous poet, Omar Khayyam, around 1100, who wrote the famous poem, the Rubaiyat. Okay, there were others. And so they took the ancient Greek works, they translated them into Arabic. They took the Hindu works, they studied them, they gathered together. Baghdad was the great center of learning for them, and it took over from Alexandria as being the dominant place of learning in the world. Okay, so from probably an 800-year period, Alexandria was the main city in terms of intellectual content in the ancient world, and then after that, Baghdad. Athens would have been in there a little bit. Athens contributed a little bit, but Alexandria overshone it, and then Baghdad. It was only much later that things moved to Europe. Okay, so what were they interested in? Well, they were interested in algebra. They were interested in some geometry. They investigated the parallel postulate. They were very interested in astronomy. Okay. That was probably their favorite thing. And Ptolemy's Almagest was like a Bible to the Arabs. They studied it intensely. And because of their knowledge of astronomy, they developed trigonometry. And they made very important advances in trigonometry. A lot of the trigonometry that you learn in school is essentially Arab work. And it's rather interesting that the story of trigonometry arises in the context from astronomy. And it's not plane trigonometry that was of interest to them. That was relatively boring. What was really interesting was trigonometry on a sphere. Why? Well, because the heavens obviously were a sphere. You we'll go outside on the night sky, you see that the sphere is obviously rotating around you. The sun comes up there, and then it comes down there. The moon comes up there. The whole stars are all rotating around as you watch in the evening. And the next day, the sun's back there again, where it left there and it came back. So obviously there's a big sphere, and it's rotating around the Earth, and it's got all the stars and the sun and the moon on it. But the sun and the moon are not fixed. They're more or less fixed, but they kind of move. It's not so easy to figure out what the sun's doing because you can't exactly stare at it, and you don't know where it is. When you look at it, you can't see the stars. But you can figure out what the sun is doing, and you can figure out what the moon is doing too if you study it for a while. Okay. But what's much harder to figure out is the planets. Aside from the stars, the moon, and the sun, there are also these 5 planets, which are like big stars, but they're not stars because they move around. They move around against the background of the fixed stars. And this was a subject of interest to almost every major ancient civilization. The Mayans, the Aztecs, the Incas, the Cambodians, the Chinese, everyone was interested in the night sky and figuring out what is actually going on up there. In fact, it's easily the most important historical problem in the physical sciences, to figure out what's going on with the night sky, in particular what's going on with the planets. Because when you watch the planets, so here are all the stars, you watch the planet over many weeks, so there's maybe Mars, okay, and then maybe a little while later it's over there, and then a little while later it's over there, and then a little while later it's over there, and you think you got the pattern, and then it doubles back on you and starts doing something else. Okay, so if you watch it over a long period of time, it makes some kind of weird motion that's very hard to figure out. And all ancient peoples were, because they spent a lot of time outside, at the night there wasn't discos and things to do. So people would spend a lot of time looking at the night sky, and they would be very interested in trying to figure out, my grandfather said that he can remember when Mars was over there, They would pass on this knowledge and try to figure out what was going on. It was easily the most important problem in the physical sciences. And almost every ancient civilization was interested, and the Arabs were very interested too. And because of that, when you're studying it, first of all, you have to map the sphere out. You have to say where things are. So you have to have a kind of a coordinate system on the sphere. You've really got to do geometry or trigonometry on the sphere. And that's where it's rather surprising that the origins of trigonometry are in spherical trigonometry, not planar trigonometry. So the Arabs discovered what we now call the sine law, what we now call the cosine law, but they discovered it in the spherical trigonometry first. On the sphere. What does that look like? Well, let's say you have there's a sphere, and you have a triangle. So you have 3 points, which you can think of as 3 stars, and you have 3 great circles through them. Those are the analogs of straight lines. So those are like equatorial circles. So they make a spherical triangle. There it is right there. And how do you measure the triangles? Well, you can measure the angles just as before, so let's call that angle A. And you can measure the sides. One of the good ways of measuring the sides is also through an angle. So if there's the center of the sphere, you can kind of look at that segment, and there's an angle there. And you can measure that distance by saying, well, that's just an angle. So everything becomes angles. That's an angle, that's an angle, that's an angle, and you have 3 angles here, capital B and capital C. And spherical trigonometry is concerned with the relationship between those 6 numbers. For example, the sine law is sine A over sine A equals sine B over sine B equals sine C over sine C. That's the sine law. And what's the cosine law? It's that cosine A equals cosine B cosine C plus sine A sine B sine A, oh there's BC, sorry, sine B, yeah, sine B sine C. So it's sort of this one here. Cosine A equals cosine B times cosine C plus sine B times sine C times cosine of this angle. That's the cosine law. Those have been known by the Arab mathematicians. Now it turns out that the planar trigonometric laws that you learn in school are limiting cases of the spherical ones. If the triangle is very, very small, then it's essentially flat. And then you get in a limit, you can, if you take sort of power series expansions of cosine and sine, then you get the traditional planar trigonometric laws as a consequence. But in fact, they weren't exactly explicitly written out, as far as I know, until about 500 years later. Around 1500 did people finally write down the planar trigonometric laws. The Arabs knew them before. Okay, we're going to talk about Arab work in equations later. But algebra is a very important introduction, a very important thing that was initiated by Al-Khwarizmi. He wrote a book called, well, in Arabic it has words Algebra in it somewhere. And then later on the Europeans read this as algebra. And so we get algebra from the title of Al-Khwarizmi's book on algebra, where he introduces symbols that we work with. Right? The whole idea of working with x's and y's as representing numbers, being able to manipulate x's and y's as if they were numbers, that's algebra. That was an Arab idea, very powerful idea, an important idea. And Al-Khwarizmi, in fact, also gives his name to the word algorithm. That comes also. Al-Khwarizmi, algorithm. It's those are connected. All right, so we're going to talk more about their work in solving equations next time. But I want to finish off what I was saying about the Hindu-Arabic number system. So the Hindu-Arabic number system came from India. Our numbers, like 405. They came from India to the Arabs. And then the Arabs brought them to Europe via Spain and other places, eventually to Europe. So we get our number system in the modern world through this link. And so first of all, people in Europe, because the numbers came from Arabia, they sometimes said this was the Arabic system, which is not entirely correct. It's actually a Hindu system, but the Arabs made important additional contribution to that number system. So they certainly deserve to have their name on it too, because they extended the number system to include decimals. They figured out how to think about decimals as part of the Hindu number system. And a very spectacular example of that is later Al-Kashi in 1430 figured out that pi is roughly 3.14159265358979932, which was by far a better approximation than anybody had ever written before that. Okay, so if you're doing arithmetic with Roman numerals, and then someone comes along and explains to you the Hindu-Arabic number system, the one that we have now, what are you going to do? Well, what did the Europeans do? It took them a long time to accept this. Okay? There was an important fellow called Leonardo of Pisa, who lived around 1200, I suppose, whose name has a nickname, Fibonacci, for which he's more well known. He's the discoverer of Fibonacci numbers. He was a leading mathematician around that time, the medieval period. He went around. He heard about these Hindu-Arabic numbers. He thought he knew this was a good idea. And he went around to Europe lecturing, telling people, you've got to work with this system. It's so much easier. It's so much better. You can do everything much faster. Here's how you do arithmetic. Here's how you do multiplication. Here's how you do division. He learned all these things and tried to teach people. Did they listen? Not really. It sort of went in one ear and out the other. And for the next 300 years, they just kept on going with the silly Roman numerals. It was only around 1500 that finally, probably merchants in Venice started using them so much that everybody else had to kind of get on board. And then there was I think a lot of the explosion of European activity after the years 1500. A lot of it's due to finally having a number system in place where you can do calculations quickly, efficiently, that you can teach young people how to do them, which is what we do now. It's an incredibly important advance. I have a lot of sympathy for Leonardo da Pisa. Sometimes I feel like a version of him because I go around telling people about rational trigonometry, how much simpler rational trigonometry is. You can do everything much simpler. It's dramatically easier. But people are not happy to change. People are very set in their ways. That's always the way it has been. So next time we're going to carry on with the Arab contribution, especially in the direction of equations. We're going to see how they solved equations. And we're going to move to the European period, how to solve particularly the cubic equations. The Arabs, the Hindus, they knew how quadratic equations. The Chinese knew quadratic equations. Cubic equations were the next big hurdle. So that's what we'll do next time.